Now on to the next concept within the grade 12 course. This concept is called recursion. To understand recursion, one must first understand recursion. Yes, that is one of the myriad of random terrible recursion jokes. If you Google recursion on the internet, there's an infinite supply of these things. We're going to ignore them for now because they're all cheesy. They're worse than dad jokes. Uncle jokes even. So, the reason why we covered stacks before we covered recursion is because they're directly applicable. So in order to fully understand what we're about to talk about, we need to venture into the idea of memory for a second. Now we've talked about the basics of how RAM works and how data is stored, but we kept it very general. Now I'm going to make it a little bit more specific today. So there are two areas our data from our programs is actually stored. The first area is called the heap. Typically, this is for global variables that are permanent. Essentially, we have unlimited size in the heap. You might think, well, we're limited by our RAM, but we're actually not. Because what happens is the operating system itself will actually take the data from the RAM, swap it into the hard drive, and take that hard drive data, put it back in the RAM, and go back and forth. This is a process called paging. And that happens. And when it goes from the hard drive to the RAM and back and forth, that's why you get lag in your programs, because hard drives are inherently really slow. So anyways, your global variables and things like that are typically stored on the heap. The stack, aka called the call stack, this is for temporary variables created in a subprogram, so your local variables and your parameters. This is super limited in size, a lot more limited than you think it is. It's called the call stack because every time we call a subprogram, it gets pushed onto the stack, it and all of its data. Now, when I say it and all of its data, I mean there's actually a bit of memory overhead for the function call itself. So let's say it has a couple integer variables. Let's say there's two integer variables, which we know take up 32 bits of data. And then there's a little bit of extra. So we have 64 bits of data there. Plus there's a little bit of extra that's added to that to remember where that function was called from. And that's basically what it's doing. So you can create it you can think of it as like a little compartment that's designated for that function call and its data. All right. So if you want a more complete explanation of the heap versus the stack, you go to this link here, and it actually simplifies it quite a bit. I've simplified it even further here because it's not really the core of what we're doing. So let's demonstrate how this stack actually works with a fairly simple program. So all this subprogram does is calculate the perimeter of an isosceles triangle. Now, given the base of that triangle and the height of that triangle, we're going to calculate the perimeter. All right. Now that assumes that the two sides that we don't know are the isosceles, the equal length sides. Okay. So what's it do? Private static void. Inside of here, we say perimeter is equal to calc try perimeter, and we're passing in a base of 8 and a height of 4, and then it just displays that perimeter on the screen. So when it gets to this calc try perimeter, it jumps down into the calc try perimeter subprogram. And it has its t base and its t height, which the 8 and the 4 get copied into. And then it calculates the perimeter as the base of the triangle plus 2 times calc side length. Now, since it's an isosceles triangle, this works perfectly fine. And obviously, when we're calculating calc side length, it's going to be using Pythagorean theorem, which means we need half that base and then the height. And so then that represents side A and side B of our triangle, and then we're going to calculate side C, which is the hypotenuse of the triangle, to get that side length. Now, if you didn't follow that, draw a picture of a triangle and pause the video and go take a look at what we actually mean there, okay? Now, what you need to realize here is every single time a method is called, it and its local data are added to the call stack. They're pushed onto the call stack, taking up slightly more than the variable sizes alone. Now, depending on the language you're working with, every language implements its own call stack. So the compiler implements its own call stack. So some languages reserve more space for the call stack than others. And some languages take up more overhead for each function call than others. So I'm not going to even specify what those values are because this isn't specific to C#. This idea of a call stack, it works in any language. So let's look at the flow of all this program. So as the program is coming down, we get into this calc try perimeter thing. And as soon as we get to this calc try perimeter call, immediately, CTP, it creates an area for CTP, calc try perimeter, and it's two variables. We've designated this as the green area. So now that's on the stack. So as soon as we come in here, this is going to return a result which is tbase, which is just a variable, plus 2 times, we don't know what calc_side_length is. So calc_side_length is another function call. So it now gets added to the stack as well. CTP hasn't ended yet. Calc_side_length is now on top of it, so it gets handled first. So now we're down into calc_side_length. And now we're looking at, now we have more operations. We got to take the square root of something. Okay, what are we taking the square root of something? We got to take the square root of, a POW operation. Okay, so let's do that POW operation. The POW operation has a base and an exponent. So what happens with that? Well, that base and exponent is calculated. When it's calculated, that value, it gets put back down into that square root function. So now that first math.pow is calculated, and now we're moving on to the second math.pow, and it gets put back on the stack. Another one, a different one, gets put on the stack this time with different bases and exponents. It gets calculated, and when it's done, its result gets sent back down to what called it, which was that square root function. That square root function can now calculate its result because its insides are complete. So it's going to calculate whatever its value is, and then when it's done, it's going to pass its result. We have this return statement. It's going to pass its result back up the chain, or in this case, down the stack, down to the calc_side_length, calc_side_length. So now calc_side_length can finish its calculation and pass its data back up the ladder as well. And now we're back in the original code, calc_try_perimeter. It can finally calculate its result, and when it's done, it's going to send its data back to the original call. Boop. And we're all done. And you can see the call stack is empty. So every time we called another function, it just piled on top, on top, on top. When it was evaluated, it got popped off, and the result given back to whatever called it. So we push, we push, we push. So what this does is this creates a system where in math terms, we always work from the inside of the brackets out. That's how it works. So maybe you didn't get that. So let's take another look at it from another angle. Now, if we're looking at that exact same system, we're going to look at the exact same code. So each method call is pushed onto the stack. As it completes, it's popped. So again, CTP represents calc_try_perimeter, and CSL represents calc_side_length. So in the very beginning, we have our call stack. Each one of these yellow buckets represents the current state of the call stack. So in the very beginning, the call stack's empty. So the first thing that happens is we're going to push the main onto the call stack, because that is a function call. And as soon as we get into there, the next thing it does is it calls calc_try_perimeter. So it gets pushed onto the stack. Well, inside of calc_try_perimeter, it calls calc_side_length. So that gets pushed onto the stack. Inside of calc_side_length, it says, I need to calculate a square root. So the square root's pushed onto the stack. Well, the square root says, I need to calculate the power of that first side first. I need to calculate the exponent, the square of that power. So the POW is pushed onto the stack. But then that POW completes, so it's popped off the stack. And then the next POW gets pushed onto the stack. And then that one completes, so it's popped off, and its results are sent down to square root. Square root finishes, so it can be popped off the stack. And then the calc_side_length finishes, so it can be popped off the stack. The calc_try_perimeter finishes, so it can be popped off the stack. And now we're back down to the main. And when the main's done, the whole program's done, so it gets popped off the stack. So we end exactly where we began, with an empty call stack. And that's how this whole operation works. We can see these function calls building on top of one another until they complete. And then they're popped off, and the result is passed back down the stack, back down to the top element on the stack. All right, so now that we understand how the stack works, let's figure out why we just did all that. Let's pause for a second. What you see in here is a completely useless function that doesn't do much. What does it do? Well, let's look at this. Private int foo. You pass in an integer n, and if that n is less than or equal to 0, so if it's a negative number, return 1. Otherwise, return foo of n. What's the problem? Why is this an issue? Pause the video and think about it for a second. What is the problem? So the problem is we're calling foo inside of foo. So it's going to say, okay, pass in n, Well, let's say n is 3. So it's going to fail the if statement, and it's going to say return foo of 3. So it's going to come back in. 3, n is still 3. Well, it's not less than or equal to 0. Return foo of 3. So what we've created here is an infinite loop. For any positive value n, we've just created an infinite loop without using a loop. We did it with function calls. Well, that's not a good thing. So this will actually crash our program eventually. What happens is, every time we add another one of these functions onto the call stack, it's taking up more memory. It's taking up memory for that n parameter, but it's also taking up that little bit of overhead for the function call itself. So we'll actually end up with an error called a stack overflow error. We've overflowed the stack. It's like putting too much water in the cup. We've filled it over. We've overflowed it. Yes, that is exactly where the website gets its name, Stack Overflow. So, that infinite loop, we see this. What if we make one small change? Instead of passing in foo of n, now we're going to pass in foo of n minus 1. So think about this for a second. What effect will this actually have? Will it change anything at all? Well, if n starts at 3, if we go in here, we see, well, is 3 less than 0? No, it's greater. So we're going to try foo of n minus 1. So foo of 2. So it comes in here. Is 2 less than or equal to 0? No. We're going to try it again. Foo of 1. Is 1 less than or equal to 0? No. Now we're going to try foo of 0. Is 0 less than or equal to 0? Yes, it is. So it's going to return a 1, which then returns it back up the chain. So that this function call gets popped off the stack. And then the previous one gets popped off and popped off and popped off until we end up way back at the beginning. So that return statement keeps getting sent back down the stack. So our effect is, instead of a infinite loop, we end up with something more akin to a spiral. It works its way down to a point. And then when it gets there, it reverses the spiral and sends it back out to the outside where it was originally called. So this is the general idea. It's a complete loop versus a spiral, an ending point. It has to have an ending point, otherwise it's no good. Introducing recursion. Recursion is when a method calls itself on a smaller version of the same problem. So we have to be careful about how we actually word this. So I'm going to come back to this, but let's go through the definition one more time. Recursion is when a method calls itself on a smaller version of the same problem. Now, if you just call yourself, so if we look at this first one on the left here, this is not recursion. It's not recursion because, yes, it calls itself, but it hasn't reduced the problem. We haven't worked towards that ending condition. That's what we need to do. The smaller version of the problem needs to work towards that ending condition. And if it doesn't, it's not recursive. Over here on the right, we are working towards that ending condition. We're getting closer to that value of 0 every single step. Hence the spiral decreasing and decreasing and decreasing. So recursion is when a method calls itself on a smaller version of the same problem. Every recursive method is made up of 2 required parts. At least one base case, that's that ending condition that we saw. This is the code that tells it to end. And the recursive case. This is the code that calls itself, hopefully with a reduced version of the problem. So let's talk about a simplified example that you might think of at home. The idea of eat your dinner. Your parents come to you and say, eat your dinner. So that's fine. You sit down, you look at your plate, and you say, well, if my plate is empty, I don't have to do anything anymore. I'm done. That's your base case. However, if there's still food on your plate, that means you're going to eat one bite. You're going to take one bite. You're going to step towards that empty plate. And then you're going to eat your dinner. You're going to do it again. You're going to restart the process. So it goes back to step number 1 again. It says, well, if your plate is empty, stop eating. Okay, if it's not, take another bite. We're reducing the problem every single step. We're getting towards that end goal. Now, big note here, failing to reach that base case results in what we call infinite recursion, very similar to an infinite loop. So when you have infinite recursion, though, it doesn't just go on forever. You're actually going to get a stack overflow because of all that overhead of every function call that's getting thrown on the stack. So here's the truth about recursion. The sad truth. Recursion is not useful very often. It really isn't. We normally only use it in problems that involve tree structures and backtracking. So things like sorting and searching algorithms, a lot of them, and a lot of artificial intelligence algorithms like pathfinding, maze construction and stuff like that, those use it a lot. But in normal day-to-day programming, you're probably not going to use recursion a whole lot. Very rarely, actually. So if you're, say, for example, a web developer, you're never going to use recursion. If you are somebody who's working in AI, yeah, you're going to probably use it a lot. Depends on where your goals lie. But when it is useful, it can produce an extremely elegant solution to an otherwise complex and ugly problem. We only use recursion when it actually makes sense to break up the problem into smaller solvable versions of the same problem. So that's that idea of reducing the problem into smaller versions of the same problem. So this is often referred to as divide and conquer. So we break it up into smaller chunks, and then we solve those smaller chunks, and then we reassemble it back into a solution to the final answer. Divide and conquer. Anything you can do with recursion, you can do with a loop. You can do it iteratively. Absolutely everything. There is no exception to that rule. So you might say, well, why even do it? Well, because it does create those nice, elegant solutions. Now, that's not to say that elegant means efficient. Sometimes recursion can be extremely inefficient, especially when it comes to memory management, because we have to deal with the fact that it's taking up all that overhead every single step of the way. So you got to be very conscious of what's going on the stack. So you got to be clear about what kind of memory is created and destroyed every step of that, every level of recursion. You go deeper and deeper and deeper. So let's compare some iterative versus recursive. Now, if you don't know what this term is, this is the term, mathematical term factorial, n factorial. Factorial is basically whatever the value n is, multiply it until you get down to 1. So if you have 4 factorial, that's the same as 4 times 3 times 2 times 1, which is 4 times 3, which is 12, times 2 is 24, times 1 is still 24. So that's what n factorial means. Now there's a couple rules with factorial. When you have 1 factorial, that's equal to 1. If you have 0 factorial, that's also equal to 1. So these are true no matter what. Okay? So if the user asks, what's the value of 1 factorial, your response is immediately a 1. So an iterative solution to this is pretty straightforward. You just build a loop. You start at the number that you asked, and you work your way down until you get to 1. Pretty straightforward. So int result equals 1. Every step of the way, we're going to multiply result by the current value of I. So it's going to be 1 times 4, then 1 times 3, then 1 times 2. I don't need to do 1 times 1 because that would be redundant. And then when you're all done, you just return the result. This is a pretty small program. Private int fact. Okay. The recursive solution is not that much smaller, but it is a little cleaner and probably a little bit easier to understand. Let's take a look. Private int fact, int n. If n is less than or equal to 1, return 1. Otherwise, return n times factorial n minus 1. So if you cannot come up with an expression where your recursion, where you have to create an expression that calls itself on a smaller version of the problem that's working towards the end goal, then you're not getting a recursive solution. Okay? So here's our base case. If n is less than or equal to 1. So we know this because of these two rules that we were given at the top. So 1 gives us 1, 0 also gives us 1. So we return a 1 in both those cases. In all other cases, we know that it is the current value of n multiplied by the next level of factorial. Because if you look at this, look at 4 factorial is the same thing as 4 times 3 factorial. Huh. Well, that's pretty interesting. So that in itself tells us that we need recursion. So let's analyze this a little bit. Let's look at the call stack and how this operation works with the call stack. So the call stack is the foundation of how recursion works. It's how we go through layer by layer and then get the result back at the end. This is what creates that spiral effect. We build it up, and then we break it back down. So each recursive call is pushed onto the stack with its own data. When it all finishes, it's popped off and it returns its result to the function call below it on the call stack. Eventually, this will return the result back to the first call. So looking at over here on the left, we have a main that says console.writeLine factorial 4. So that means n has a value of 4. Now, if we go through this code, we say, is 4 less than or equal to 1? No. So the result is going to be, immediately, we're calling factorial 4, so it goes into the recursive case, which is 4 times factorial 3. Well, that means factorial 3 gets pushed onto the stack. And now it comes in again and says, well, is 3 less than or equal to 1? No, it's not. So we're going to return 3 times factorial 2. So that means factorial 2 now gets pushed onto the stack. And it comes back in, is 2 less than or equal to 1? No, it's not. So it comes in, we have to go to the recursive step again. And this is going to be 2 times factorial, 2 times factorial of 1. Right? And then finally, we get push factorial 1 onto the stack, and it comes in, is 1 less than or equal to 1? Yeah, it is. So we finally get to a base case. We return 1. So this 1 doesn't go any more deep. We're not going to be adding any more to the call stack. So now it starts unwinding itself. It returns the values down the chain. So fact 1 gets popped off the stack, and the 1 gets pushed down, gets put onto the previous call. It gets returned down to the previous call. So now the math, instead of 2 times fact 1, is 2 times 1. So this evaluates itself and becomes a 2, and then fact 2 gets popped off the stack, and that 2 gets pushed down to the next one. So now we have fact 3, and that's 3 times 2, which is, of course, 6. So fact 3 gets popped off the stack, so we have our answer is 6, and that gets returned down to the fact 4. So we have 4 times 6. We does the math, we get 24. So this one completes. We've finally done this last operation. So when it returns, it's going to come all the way back up to the original call of fact 4. Doop. And that 24 gets returned as a result. So every layer of recursion pushed it onto the stack. When it finished evaluating itself, it popped itself off the stack and returned its result to the element below it on the stack. That's the way to think about how this whole thing works. Oops. So how do we actually do it? And this brings us to that divide and conquer thing that we talked about. Divide the problems into subproblems of the same type as the original. Looking at this previous example, you can see how we broke it down into n times the slightly smaller version of the same problem. A common mistake here is to use the subprogram calls as basic iteration. That's not what we're doing here. So for example, a string analysis problem that simply removes the front letter and then calls the function again, this is just a loop. This is just a for loop in another form. It's not really recursive because we're not reducing it down to the same problem. We're just iterating in that case. You're just saying, look at the first letter. Okay, now look at this next letter. Now look at the next letter. That's not a recursive solution. That's an iterative solution. It just happens to look like a recursive solution. So solve each subproblem. When you're done, combine the results back up. So factorials, can we define the problem with calls to the problem itself? Well, that's where we look at the math. And I talked about this a second ago. 4 factorial is the same as 4 times 3 factorial. So let's break that into general terms. If we want to break up n factorial into its subproblems, we know that n factorial is equal to n times n minus 1 factorial. Well, n minus 1 factorial is equal to n minus 1 times n minus 2 factorial. So we can see how the math itself keeps expanding, and it goes on and on and on and on and on until we get to a base case. So here we can see each step is the same problem, but it's closer to that base case every single time of n is equal to 1 or 0. So let's do a quick recap. What is a recursive function? Well, what's in a recursive function? One or more base cases. Now you may find certain problems. So for example, we saw this one has, in the previous one we saw n is equal to 1 or n is equal to 0. We just happen to be able to group those into a single check. But there are 2 different base cases really. So these are the cases that occur when the problem is broken down into its smallest point. No more recursion is required. It's truth by definition. You can also have one or more recursive cases. Yes, it is possible because you may need to split off and do more than one thing. You may actually call something recursively more than once in the same recursive solution. There's nothing wrong with that. It may be pretty inefficient, but there's nothing technically wrong with it. So this is when we step towards the base case. We have to break down the problem and work towards that base case. If we're not, then we're not creating a recursive solution. The method calls itself on this smaller version of this problem. Makes sense. So looking at this code, we can see the base case is that first if chunk of n is equal to 1 or 0. And of course, the recursive case is that final step at the very, very, very end. So here's some tips. Number 1, make sure the recursion stops. It must have a base case that will be reached at some point. You'd be surprised how often this doesn't occur, and this is where you end up with that Stack Overflow error. You make a logic error. Very simple. Limit recursion to 1 or 2 recursive methods. What do I mean by this? Don't have something like A calls B, which calls C, which then calls A again. So yes, technically that is recursive. It's daisy chains down until it gets back up to A. This is a little too deep. I wouldn't go much more than A calls B, which then calls A. That's about where I would go, because if you have A calls B calls C, that's 3 things that are going on the stack before the recursiveness kicks in. And that's going to be very expensive, right? That's too much. So try and avoid that whenever you can. That doesn't mean that it's not necessary in some situations. And in fact, you might see this in your next major portfolio task. You will, get Stack Overflow errors because the base case may not be hit before you run out of the stack space. So your solution may be fine, may be absolutely fine, but that doesn't mean that, your solution may be completely fine, but that doesn't mean that it's a good recursive solution or good to use a recursive solution, because it may go too deep in terms of the stack. So what's going to happen is you're going to find in your homework and your minor portfolio tasks coming up that one of them specifically is going to crash your program if you go too far. And the reason being is that every recursive step doubles in scale, doubles the size on the stack. And that's a problem, obviously. So you're going to run out of stack space in a big hurry. So just because you have a solution that's technically correct, it may still fail because you just don't simply have enough stack space for it. And then only use recursion when you're asked to, or for problems where it's worth it. So there's times that I'm going to ask you to do recursion where you know full well that there are better iterative solutions. But I'm asking you to do recursion because I want to see that you can actually do the recursion, that you can design a recursive solution, that you can implement a recursive solution. Not just come up with a problem, or come up with a solution to the problem, right? So, and then of course, you also should use it for problems where it's actually worth it. And you're going to see a number of these when we get into searching and sorting. Finally, do not use global variables in your recursive methods. I cannot emphasize this enough. The problem is you don't know which level of recursion is manipulating that data. And that is not a good thing. Because you're going to end up with problems where one level of recursion is expecting the data to be one thing, but then the next level comes in and manipulates that data, and by the time it pops off, that previous level is now wrong. It doesn't work anymore. So do not use global variables in your recursive algorithms. Your recursive algorithms should be self-contained and work with the data that they have and the data that's passed in only. And that's recursion in a nutshell. I've given you some pretty basic things to start off your homework with just to get your feet wet, and then they're going to progress as you get into the practice work a little bit more and more and more each step of the way. Good luck and have fun.